Let's see if I can get this going again. All right, so in theory, I'm sharing my screen again. So in order to have stereoselectivity, we would need to have a difference between the energy of attack from each face. So here's our question: is there stereoselectivity, right? So let's draw that carbocation. And the carbocation intermediate would have had the methyl group back here, and the hydrogen there. And then we've got a planar carbocation here that basically has a p orbital, right? So if we were to draw that in its most stable conformation, this methyl group is going to be in the envelope part of the cyclopentane. So we draw the cyclopentane like this, right? The methyl group will be sticking out there, the hydrogen will be sticking up like that. So the methyl group's kind of out of the way, and then our carbocation is on this carbon. So it probably does attack a little bit more from the bottom, right? Because there's no steric hindrance. There's a little bit maybe of steric hindrance on the top face, but it's far enough away and it's only hydrogen that it's probably not really blocking very much. And keep in mind that that's just that conformer. There's relatively reasonable conformational mobility. So this thing will also take additional conformers where maybe that top face is not being blocked as much, right? And this is kind of over the middle of this bond, not right over there because it's an odd numbered ring. So there's not really a transannular interaction. You can't have transannular interactions with odd numbered rings. So if this methyl group was forced into that position, then you would expect to see the top face being more hindered and you'd get preferential attack from the bottom face, but hydrogen is small. Does that answer your question, Isabel?
Yeah, that makes sense. Thank you.
Yep. So if you wanted to, you could say that there might be a little bit more, right, maybe a little bit more of the cis isomer than the trans isomer. But it's not going to be a huge difference. Other questions on the quiz? How did it go? My guess is not famously, because the first time through this, it usually doesn't go famously. You should write out those mechanisms, pick a different substrate, go through problem 39, write out the mechanism for an Sn1 reaction multiple times, write out the mechanism for an Sn2 reaction multiple times until you get really comfortable so that you can write that mechanism pretty quickly. Because as we get into discussing solvent effects and sterics and other things, you're going to need to use the mechanism in order to explain the result. So if you can't write the mechanism fairly quickly, then you won't have enough time to talk about the solvent effects. So what's going to go on is you have hopefully watched the video about leaving groups, so you know what makes a good leaving group. You've watched the video about substrate structure, so you'll notice that this was a secondary substrate, right? And secondary substrates can go by either Sn1 or Sn2 pathway depending on the other conditions, solvent, nucleophile strength, things like that. You watch the video on nucleophile strength, that will be the subject of Thursday's quiz. I'm going to give you pairs of nucleophiles and ask you to choose the better nucleophile and tell me why that's the better nucleophile, right? There are 3 things that affect nucleophile strength. There's basicity, in general, stronger bases are better nucleophiles. There's polarizability, that's relevant in neutral nucleophiles. The more polarizable atom can reach out with its electrons at a larger internuclear distance and start forming a bond. So sulfur and phosphorus are better nucleophiles than oxygen and nitrogen for neutral nucleophiles. And then there's solvation. If your nucleophile is a hard, negatively charged atom that is very small and can be solvated very strongly with a strong ion dipole force, then it's less able to react, so that solvent effect. So I'll give you a series of nucleophiles. You'll identify which of those three effects is the one that's most important in that particular case. Choose the nucleophile, draw whatever pictures are necessary to explain your result. Next Tuesday will be the quiz on solvent effects, which is probably the most complicated and difficult to grasp, right? So you'll need to be able to write the mechanisms quickly and easily so that you can talk about how the solvent is going to affect the energy of the various species along your reaction coordinate. So there are 3 videos on solvent effects, 2 on polar protic solvents, one talking about the Sn2 reaction rate, one talking about the Sn1 reaction rate, and then there's one on polar aprotic solvents, which enhance the rate of the Sn2 reaction, which is why that reaction of sodium fluoride in DMSO, which is one of the polar aprotic solvents, went by the Sn2 pathway, even though it's a secondary substrate and could have just lost the leaving group spontaneously. So that'll be the quiz next Tuesday on those next 3 videos that you're going to watch for Thursday. And then after that, we'll introduce elimination. So for next Tuesday, you're going to be watching the videos on elimination, and then next Thursday, there'll be a quiz on elimination, which will look a lot like this one, except it'll ask you exactly the same questions for the E1 versus E2 elimination as I just asked you for Sn1.